Welcome to the video introduction to Module 5. In the last two modules, we learned how to make and interpret confidence intervals and hypothesis tests based on simulation methods. In this module, we will learn an alternative method for performing statistical inference that will not require simulations. This video will talk about section 5.1 of the textbook, which introduces normal distributions and how to use them to calculate areas and percentiles. The simulated sampling, bootstrap, and randomization distributions that we've been using in the previous two chapters have all had a sort of similar bell shape to them. These simulated distributions will, in this chapter, start being modeled using smooth bell-shaped curves called normal distribution density curves. And when working with normal distribution density curves, instead of looking at the proportion of dots in a particular region, like we did with the simulated distributions, we'll look at the proportion of the total area that is under the curve in that region. Normal distributions are symmetric, bell-shaped density curves. Now there's not just one normal distribution, there is in fact a whole family of normal distributions, and we distinguish between the members of the family based on what the mean and the standard deviation of the distribution are. So when we talk about a density curve, what do we mean? With a density curve, the total area under the curve is always going to be equal to 1. That's the decimal equivalent to 100% of the distribution is under the density curve. And the proportion of the distribution in any interval is equal to the area under the curve over that interval. There's something very important that all normal distributions have in common. They all have the same density. That is, the proportion of the total area that's within one standard deviation of the mean is the same for all normal distributions. So even though they may have this different means, we denote the mean by mu, remember, and they may have different standard deviations, the proportion of the area within one standard deviation is the same for all normal distributions. And the proportion of the total area that's more than 2 standard deviations greater than the mean is the same for all normal distributions, and so on. Now when we're talking about normal distributions, we have a little bit of notation shorthand we do, so we don't have to write out the words normal distribution with mean equal to mu, blah, blah, blah. And this is our notation. So we have n for normal, and then to know which normal distribution we're working with, we need to know what the mean is. So in parentheses, we first write the mean, and next we write the standard deviation, sigma. So for instance, if IQ scores have a normal distribution with a mean equal to 100 and a standard deviation equal to 15, I could write that as n for normal, mean 100, standard deviation 15, and that would be my shorthand. Now, I said that the proportion of the population that falls within a certain range, say between A and B, is equal to the area under the distribution curve between A and B. So that's that shaded blue area here. And the question becomes, okay, so if we want to figure out what proportion of the population that is, how can we find areas under the density curve? Now, if you have taken calculus, you probably remember that the way that we can find area under a curve is by integrating the function that describes the curve, and that's what this is over here. It's the function that describes the the normal distribution curve with a mean of mu and a standard deviation of sigma, and we'd integrate from A to B. We don't want to do that. That's a really ugly function. It's very difficult to integrate. And because it's one that's used so often, technology has been developed to find these areas for us. And there are lots of different types of technology that can be used. There are all kinds of online applets. Most calculators can do it. But the tool that we are going to use in this course is StatKey. And there is a separate video showing how to use StatKey to find areas and cutoffs using the standard normal using any normal distribution. We'll get to standard normal in a minute. So make sure you check out that video. Now, I mentioned that normal distributions all have the same density, and so the proportion that would be within one standard deviation of the mean is the same for all normal distributions. Here are 3 normal distributions. They all have different means and different standard deviations, but within one standard deviation of the mean, we have about 68% of the area for all 3 of these distributions. So all that really matters when we're trying to figure out areas is the number of standard deviations that our values are, where we're defining this range from A to B. How far are those from the mean? And we can measure that with z-scores. Now, there is one special member of the normal distribution family. It's the only one that has its own name. I accidentally said it earlier. It's called the standard normal distribution. And it's the normal distribution that has a mean equal to 0 and a standard deviation equal to 1. Now, the standard deviation is also referred to as the z-distribution, because if we take any normal distribution with a mean mu and a standard deviation sigma, if we calculate the z-scores, so take our values, subtract the mean, and divide by the standard deviation, then those z-scores are always going to have a standard normal distribution. And so in order to find areas, one way we can do it is by just using the applets. The other way is by standardizing the endpoints that we're using and then using a standard normal z-distribution. You can look for how to do this in section 5.1. So what are the goals in working with normal distributions? Well, we said that bootstrap distributions tended to have a normal distribution, and so if we can approximate a bootstrap distribution with a normal, then we can construct confidence intervals based on a normal distribution instead of doing simulations. And we also learned how to do hypothesis testing, and to do that we needed a randomization distribution to find the p-value. If we can approximate the randomization distribution with a normal distribution, then we can use that normal distribution to compute a p-value for a hypothesis test. And if we can find an easy way to estimate the standard error without doing lots of simulations, we could even do this without simulating any distribution at all. And that's what we're going to be working towards in this module. In the next video, we'll start looking at how we can work with normal distributions to make confidence intervals and do hypothesis tests in a very general setting. In the following parts of the course, what we'll be doing is looking at how to use these distributions in specific situations and find formulas for calculating the standard error. So that's what's coming up. I hope this helps you get a good start on this module. Have a good day.